All right, let's go ahead and start. All of the pre-tests are open today. So the first one isn't due for another week yet. So the first one you need to have completed by next Thursday, so September 5th. You can take all of them now if you want to, or you can take them by the due dates. Those are posted on Canvas. Slack will give you reminders of due dates as they approach. Any other unit test questions? Have you found the practice questions?
Are the tests to take them multiple times or just once?
Right now we're planning on just once. Yeah.
Is there a time limit on the pretest? Like, can I open and then answer like 2 days later?
No. Testing center mandates a time limit. I'll have to double check what we have in there. Testing center limit is 75 minutes, and I think we might have these set to 50. Oh, I did have a slight miscommunication on a syllabus policy with respect to exams. So I said that each exam you had to have 60% for a passing course grade. That's the collection of the exam component. So you can do really bad on an exam and still pass the course. Yeah, it's an important distinction. All right, other announcements. So the AACHE is having their kickoff meeting tonight. So that's in how Atrium. So that's at 6 o'clock. It's a good organization to be involved in, so I encourage you to attend. And then, let's see, the first tier of homework, that's due next Wednesday. So start thinking about that pretty soon. And then, if there's nothing else, we'll go ahead and get started with the content for today. So last time we talked briefly about systems, open versus closed systems, and so we recalled what the first law of thermodynamics is, and so that's where we're going to start. So, you know, again, the first law is all about conservation of energy, and we can start writing equations down that make use of that conservation principle. Incidentally, these laws are not mathematically proven laws. They are just laws that are supported by the preponderance of the evidence that scientists and engineers have collected over 150 years. So they're principles that seem like they make sense and they may seem obvious, and they've certainly held up to the test of time with respect to experimentation. But neither the first nor the second law have a mathematical proof. Just kind of as a side note. Okay, so what are some of the different types of energy that we talked about? We talked about kinetic energy, we talked about potential energy, we also talked about internal energy. So remember, that's the more precise version of what we think of as heat. So the internal energy of a material is basically a quantitative measure of the kinetic energy of the collection of particles that comprise that material. So if we put everything together, you know, the overall first law statement is for any system, for any process, the overall change in energy, and we can put a universe subscript down there, is 0. So just a little point of notation here. So the superscript up here, that's T, and the subscript I wrote here is shorthand for the universe. So the capital delta you've seen a lot by now, so that just means a change between before and after. The superscript T in this course means an extensive property, so the total amount for a quantity. So, and that's in contrast to a specific or a molar property. So the volume of a system is the overall volume that it comprises, and so we would write V superscript T, meaning the total extensive volume, and that's as opposed to V, which doesn't have any decorations, which is going to mean the molar volume. We can relate the two fairly easily, and most of the time it's more convenient to work with the intensive version of the variable and not even worry about the number of moles. That gets you in the problems of, in certain cases, especially in open systems or in reacting systems, where the number of moles may be changing or the mass contained within a system might be changing. So we just need to be careful about that. All right, so if we break this grandiose statement that the total change of any process at the universe equals 0 down into more manageable pieces, the amount of energy that enters a system has to be equal to the amount of energy that left the universe. And so we can tally up the various different contributions to the energy that a system contains. So we have our internal energy. So a process is going to change the total internal energy of a system. And I mean capital U there. And then we can also have changes in the potential energy of a system. It's kinetic energy. And so this side means total energy change of a system for some process. And we'll talk about a specific system and some specific processes shortly here. Since the amount of the total energy change of the system has to balance out with the total energy change of the universe being 0, we can break down the two different ways, or we can break down all the various ways of transmitting energy into or out of a system into two different terms. So the first term is the heat term, and so that's transmitted heat into the system. And so if you remember when we were drawing arrows on the little process diagram that we showed on Monday, that's the heat arrow goes into the system. And the second contribution is the work. And so that might mean compression, that might mean expansion, that might mean pushing. There's a lot of different ways that work can enter or leave the system. So this is mechanical energy. Again, entering the system. All right, in a lot of different chemical engineering processes, the change in potential energy is going to be inconsequential, and the change in kinetic energy is going to be inconsequential. Counterexample might be if you're trying to do an energy balance on a rocket, something where you had stored chemical energy that's being converted into gases that are then hurling out the back of the rocket that's creating thrust, and that all that energy you're hoping to transform as efficiently as possible into a change in both potential and kinetic energy, in which case you need to hold those around. So a lot of times, though, this will be the version of the first law that we end up using. So most of the time, we're not going to be concerned about kinetic or potential energy. And the deltas imply overall changes over some macroscopic period of time or some macroscopic displacement. So if you actually want to start to put numbers to these things, we need to look at the differential form. So delta is capital delta, lowercase delta we use for differential quantities, or for a full differential, we'll use lowercase d. So if we take the full differential of ut, that's going to be equal to a differential change in heat or work. So all that means is that we've gone from big macroscopic changes into small quantities that we can start to use calculus to manipulate. And then to actually do calculations, we have to start thinking about some actual systems. So state changes, process changes in gases are an easy place to start, and they're also pretty relevant to the chemical process industry. And so that's where this thermodynamics textbook starts. So if you're assuming that you have a gas and you want to think about if something about the gas changes, how much heat does that require? How much mechanical energy does that require? So the thought experiment that we often employ for this is the piston cylinder system. And so the idea is that you have a piston that fits airtight into a closed cylinder. Can everybody see? Yeah. And we have some gas particles in here. And so what are some of the ways that we can describe that gas? We've got the temperature. Kind of familiar with that, what that means. We've got the pressure. We've got the total volume. So these are different descriptors that describe the state of the gas that's in that cylinder. You probably want to know how much gas is in there. So that's a different quantity than the total volume. And so this cylinder, let's assume that it's circular, so it has a cross-sectional area. And so you say that it has a cross-section of A, and we put a force downwards on the cylinder. So we imagine compressing the gas. So this is position 1, and this is position 2. There is going to be a change in that piston height, right? So the amount of work that's done by using a force F to compress the gas, the vertical height of dl is pretty easy to compute. So work is force times distance. So the amount of work that's done is going to be the force times the distance again. And if we want to convert this into thermodynamic variables, how much volume, what was the overall change in volume of this little process here by compressing it by a height of dl? I've lost this area right here in my sketch. So I can compute the volume of that chunk, right? So it's the cross-sectional area times the change in height, right? So that means that I can write the change in height as, and you need to remember my superscript there, is dVt over A. And so my change in, so the amount of mechanical energy that I use to do that change in volume is now expressed this way. And this F over A, that's a force over an area that's otherwise known as a pressure, right? Now I got to worry about is the sign. So I drew an arrow on the force indicating that the force was pushing that way. So I'm adding mechanical energy into the system. So would you expect the internal energy of the system to go up or down as a result of that compression? It's going to go up, right? So that means that the sign of my dW by the conventions we're using need to be positive. What happened to the volume of the gas when I compressed it? It decreased, right? So that means that my z-axis needs to be pointed up. So when my dl is applied, I know that it's negative. But however, volume, we don't really talk about positive or negative volume. We do talk about changes in volume, though. So if my dV is negative, then my work is going to be negative unless I put a negative sign in front of there. So this is kind of one of the first places that we start with thermocalcs. And so we've got enough done now to start talking about a specific system. So let's think about an exact case here where maybe we're going to put methane into our cylinder. So we want to compute a state change, let's say of 1 mole of methane. And what we're going to get a little axis drawn here. So I'm going to put P on the y-axis and V on the x-axis. And what we're going to do in this process is we're going to take our 1 mole of methane, and we're going to start right here at 10 atmospheres, and I'm going to call this state 1. And the temperature of state 1 is 298 K. And then after the process, we're going to be up here at 40 atmospheres. We'll call the initial and final volumes V sub I and V sub F, and we'll be using extensive quantities for now. We haven't calculated those volumes yet. I'm going to call this state 4 for reasons that'll become clear shortly. And now we want to think about how we're going to get from state 1 to state 4. And we'll add that the temperature at state 4 is also going to be 298 Kelvin. All right, do you remember from 210 about how for an ideal gas anyway, internal energy and enthalpy vary with pressure? For ideal gases, they don't, right? Has anyone ever explained to you physically or at a mechanistic level what distinguishes an ideal gas from a real gas? Ideal gas particles don't talk to each other. They don't repel each other. They don't attract each other. They don't even know that there's another particle that exists in the universe. And when the particles get spread out enough from each other, that's not a bad approximation because it's just mostly nothing out there. So we say when you're right around 20 liters per mole for your molar volume, you can basically neglect interatomic or intermolecular interactions. As particles start to get closer to each other, that starts to become less of a good approximation. And when the particles get close to each other, well, when they have really strong intermolecular interactions or when the pressure gets large. So for an ideal gas, the only contribution to the internal energy and in turn the enthalpy is going to be the temperature. So if I add the caveat on here, and this is probably not going to be a great approximation since we're going to be going up to 40 atmospheres. We're going to treat the methane for this example as an ideal gas. The initial state and the final state are both at 298 degrees Kelvin. So I know that no matter how I decide to get from point 1 to point 4, my total change in the internal energy of that methane is going to be a big old fat 0. So internal energy is a function of temperature only for an ideal gas. So isn't that neat? All right, if it was a real gas, this delta U would be a non-zero number. But another thing would be true is that change, this is not a function of the path taken. And so, can we see the bottom there? Not so much. So what does that mean? It means that thermodynamic properties like U or H are what we call state functions. So that means they're only a function of the state of the system. So a function of the temperature, a function of the pressure. They have no memory of previous states that can inform what the current state is. It's only those state variables, and that's pretty nice. Okay, so let's go back to our PV diagram here. So this one right here is a more compressed state. So I'm going to draw sorry, it's my more expanded state. And up here, this is a more compressed state. And we're going to consider two different pretty simple paths. So the first one, this is kind of at room temperature for starters. What we're going to do is we're going to cool it down, but we're going to keep the pressure constant. And that's pretty easy to do. We're just going to put it in a cooling bath. And this piston on top, we're just going to put a weight on it So the pressure always equilibrates at the same level of 10 atmospheres. And so we're going to call this state 2. And so that's an isobaric cooling step. So isobaric, that's constant pressure. And then after, we're going to go up to the final state. So we're going to take a process path of 1 to 2 and then 2 to 4. And so that's constant volume. Does anybody remember what a constant volume process is called? Yeah, isochoric. So that's going to be isochoric, and that's also easy to do. So as we cool, this piston is naturally going to settle as the gas cools down. And then we're going to imagine that our piston has a lock, and we're going to lock it into place. And then we're going to heat it back up to the final temperature. And automatically, the pressure should be what we wanted it to be. So this is going to be isochoric heating. So that's pretty easy. We're just going to cool it down, and then we're going to warm it up again. All right, there are a few details we need to fill in here. So in pairs of 2, I want you to work out what the missing details are for state 2. What is this volume? What temperature do we need to cool to? You're going to need to use the final state in order to inform that calculation, because you need to, first of all, you need to know what volume are you going to hit. So up here, you know the temperature, you know the pressure. So the volume you can get. Once you've got the volume, you're going to go down here to state 2 and say, okay, well, what does the temperature need to be at this volume and that pressure? Pretty straightforward, right? Okay, so just a couple of quick ideal gas calculations.
Yeah, I know. It's like, wait,
Chris, with that really, how do you, what is the volume you guys have in front of us? How is that? How is this all? I have three guys. Yeah. Okay. I just put it in your backpack. Yeah, you have it on the. That's what you try. For T4 we have, or no, for T2. Yeah, we have it. I have this. I got another. I got like the one they told me by the. I got
Okay, so first question, what is the volume at state 2 and 4? Did I give you an initial volume? You didn't ask. Do you have enough information to find the initial volume? I did tell you it was a mole, right? I did tell you 10 atmospheres. I did tell you 298 Kelvin, right? So our V1 here is going to be a good old nRT1 over P1, right? All right, what unit system should we work in? We're going to do cubic centimeters today. All right, so cubic meters, that doesn't work so well for gases usually. All right, do I have anything that does math open? Well, I do, but it's going to be really small, so you're just going to have to trust me. So 83.14 times 298. You know what? The pressure's in atmospheres, right? So let's use the atmospheres one. So 0.082. That's going to give me liters and an atmospheres for my units there. So 0.082 times 298 divided by 10 atmospheres. That's giving me 2.4 liters. All right, is that what I have written down? Yes, that is what I have written down. I didn't hear anybody jumping up and down with excitement that you had the same number as me. Yeah, 2.44 liters. And if you really want to be pedantic, I need a 0.8206 is my ideal gas constant for liters in atmospheres. But that's a good one to remember. All right, so we've got 2.44 liters. All right, so for T2, it's P1, and that's going to be V4T. V4T and V2T are the same. Equals my N, R, T2, I don't have an that's V4T, and we know that V4T is also equal to nRT4 over P4. I don't know T2 yet, but I do know everything over here. So P4 was 40 atmospheres, which is 4 times greater than 10 atmospheres. So I can rework out all this, or I can just divide this one by 4. And either way, I'm going to get out 0.61 liters is V4. And so therefore, T2 is V4T times P1 over an R. All right, I want somebody to tell me what it is. And that is pretty much what I have written down. So what I have in my notes is 74.3. So that's all going to change depending on how many digits you retain throughout the calculation. Okay, so we've got a nice little piece of information there. All right, so the $1 million question then is, let's do the energy balance on state 1 and state 2, and let's figure out how much heat was involved, how much pressure was involved. Okay, so this was cooling at constant pressure. All right, where do you start with problems like this? We can always start with the first law. So the change in the total internal energy, so dNu or dUt, is going to be equal to differential change in Q minus the differential, or plus the differential change in work, which looks like that. I can, if I want to know what the heat is, and I can just rearrange for what is the heat. So dNu, and now it's going to be plus PNdV. The rules for manipulating differentials is the same for manipulating derivatives. So the sum of the differentials is the differential of the sum. So I can also write dNu plus PNV, or more succinctly, that's UT plus PVT. This quantity right here collapses into a single quantity. You talked about in 210, remember what it is. U plus PV equals H. So this is our good friend enthalpy. So for our constant pressure cooling step, the amount of heat required, we can calculate that just by calculating what the change in enthalpy of the gas is as it compresses. And for an ideal gas, so I'm going to write out the full differential of enthalpy real quick here. So if I have, for one phase that's non-reacting, Gibbs phase rule tells me I have two independent variables. So if I choose to expand this in terms of temperature and pressure, the change in enthalpy is going to be, it's two partial derivatives multiplied by the change. So there's going to be a constant pressure part of it plus a constant temperature part of it. So for an isobaric process, this part goes away. And does anybody recognize another name that we have for that partial derivative? Change in enthalpy with respect to temperature at constant pressure. We often call that the heat capacity. or the constant pressure heat capacity. So our dq for steps 1 to 2 is going to be equal to the heat capacity times the differential change in temperature. And so if I want to know what the overall Q12 is, then I just integrate both sides if I want to get rid of the differential. So the total Q is going to be the integral of the heat capacity with respect to temperature from the initial state to the final state. All right, and we've done heat capacity integrals. Yes? So the differential pressure is going to be 0 for an isobaric process. And another reason I can do that is this is 0 for ideal gases. The enthalpy is only a function of temperature for ideal gases. But even more generally, if it's an isobaric process, that's going to go away. Okay, so how do you evaluate those? Well, you just need the heat capacity. So we can look up in the back of the book. In the appendices, back here where it says heat capacity, and we go right up into the top of the table. And we've got the equation. And for methane, we've got this entry. So the heat capacity for methane, CpIg over R. So Cp, that means constant pressure heat capacity. The superscript Ig, that means the ideal gas heat capacity. And we'll talk a little bit more about how that's distinguished between the heat capacity. The ideal gas one is the one that we're going to use in calculations over and over and over again, and then we correct for non-ideality later. So it's just a simple polynomial correlation. So if you want to calculate an integral of this thing, it's going to be A times delta T plus B times delta T squared over 2, and so on and so on. We've seen that integral before. All right. Get this in the notes. Yeah, whatever. Okay, so if I actually plug all those numbers in, then I got to remember the n in front of there because that's the extensive. So it's going to be n times my gas constant times the integral from T1 to T2 of my CpIg over R. And so if I actually plug in the numbers for methane in there, what that's going to come out to, if we do this in joules for the purposes of getting the energy, we're going to have 1 mole times 8.314 joules per mole Kelvin. So it's 1.7 for the A coefficient, and you'll get used to looking these up. So 7 plus 1/2, 9.1 times 10 to the minus 3 t squared minus 1 over 3 times 2.2 times 10 to the minus 6 t cubed evaluated between the final temperature, which is 74.3, and the initial temperature, which is 298. We evaluate that, that's going to come out to be minus 6.15 kilojoules. All right, so let's see, I've got a good amount of time left. Okay, does it make yes? Yep, so this is just the evaluation of that heat capacity formula. Yeah, that was integrated. Okay, on your own, you should work that calculation out and double check that result. Okay, so the sign on Q, that means that we took heat out of the system, and that should make sense to you. We needed to cool the gas to shrink its volume by the appropriate factor of 4, so it's ready to be heated then at constant volume to its final state. Okay, so what is the internal energy change then for that part of the process? What do we need to finish that out? So the total, we had a balance written down here. We got it, right? Or do we? We just calculated the Q part, so if we want to know the internal energy change, we got to go back to here. And what we don't have yet is the work. So how much work did it take to do that compression step? We removed the heat and we got some work along with it, right? Because the volume changed. The pressure was constant. Well, I can integrate this, right? And if the pressure is constant, then that's an easy integral. And so we're integrating with respect to volumes. The differential just turns into the delta. And so for that part, you got to remember the sign convention here. So that is going to be minus 10 atmospheres times volume 2 minus volume 1. Volume 2 was 0.61 liters. Volume 1 was 2.44 liters. And so that comes out to 17.9 atmosphere liters, and that's an interesting unit, isn't it? That converts into 1.85 kilojoules. And leaving that unit conversion to you all to work out. So the delta U for that first step in the process is going to be minus 6.15 kilojoules because we cooled it. Does the sign of the work surprise you? The work was positive. If you think about that, we did use a force. We used the force of the atmosphere to push the gas down to its final smaller volume. So even though we took out a lot more heat from the gas than we injected mechanical energy back into it, we did trade some thermal energy for mechanical energy. So that's going to be minus 6.15 kilojoules plus 1.85 kilojoules. And the total minus 6. Plus 1.85. Minus 4.3. Okay, so Friday we're going to calculate the other leg of this process and look at a different way of getting from the same two states. And then we'll move on to the next topic, talking about how do we do some energy balances on open systems.
See you later.